Hi everyone, today is our first online lesson. So we are going to continue on the chapter 3, transport layer. The last time we have already seen on the TCP header. So for today, I'm going to teach you on the next subtopic, which is TCP performance. So we know that TCP provides reliable data transfer service in the face of packet loss, which is typically results from the overflowing of router buffers as the network becomes congested. So how is congestion happen? Congestion can occur if the load on the network is greater than the capacity of the network. So in other words, each network has its own limit on the capacity, and if the sender's data rate is higher than what the network can give, this will result in the congestion. It can also happen because routers and switches have queues or buffers that hold the packets before and after processing. So we know that each of the router and switch will take some time to process the packets before it can proceed to transmit to another switch or routers. So in other words, for example, if the rate of packet arrival is higher than the packet processing rate, input queues become longer and longer. Let's see an example here. Here we have a switch. So at the switch, there are packets queuing to get to be processed by the switch. So if the switch can, for example, process the packet at very low rate, and there are many packets at the arrival which needs to be processed, so input queues here will become longer and longer. In another example, if the departure rates means the rate at which the packets at the switch is waiting to be departed or to be transmitted to the next switch or to the destination. If the departure rate is slower or is lower than packet processing rate, output queues become longer and longer. So this will also result in the congestion. So to treat the cause of this network congestion, mechanisms are needed to throttle senders in the face of network congestion. Moving on to the next slide. As I have said before, TCP must use end-to-end congestion control rather than depending on the network layer to provide congestion control. This is because network layer or IP layer will provide no explicit feedback to the end systems regarding network congestion. So TCP provides a flow control service to its applications to eliminate the possibility of the sender overflowing the receiver's buffer. So we can say that flow control is a speed matching service in which it matches the rate at which the sender is sending against the rate at which the receiving application is reading. In other words, flow control will adjust the rate the sender sending the data with the rate at the end receiver is reading the data. So at the receiver flow control, it also adapts sender data rate to the receiver speed. For example, if the receiver speed is slower than the sender data rate, it will cause congestion because the packet processing rate at the receiver could not match the rate of packet arrival. Hence, the input queues will become longer. This is just like the one that I have drawn on the previous slide, which I show you. The congestion happen at the arrival, where the input queues will become longer and longer because it couldn't match the packet processing rate at the receiver. So the receiver flow control also prevents buffer overflow at the receiver, because we know that each receiver or each switch or each router, it will have its own limit at the buffer. Okay, the assumption that the buffer is unlimited is not really a valid assumption. So we know that everything has a limit so does the buffer at the receiver. So how to do that? The first thing that the flow controller have to do is for receiver to advertise its available buffer space, or we call it RWND value. RWND means receiver window. Okay, here we can see at the receiver side buffering. Okay, so this is the receive buffer, which is the buffered data waiting to be processed at the application. So here is the receiver window, or in other words, it is called free buffer space. So receiver advertises this free buffer space by including this RWND value in the TCP header of receiver to sender segments. So sender will limit amount of data to this RWND value, and hence it will guarantee receiver buffer will not overflow. Informally, the receive window is also used to give sender an idea of how much free buffer space is available at the receiver, because we know that TCP is full duplets, so the sender at each side of the connection maintains this distinct receive window, means it has different distinct receive window value both at the sender and also at the receiver side. So we can call that this RWND value denotes the amount of spare room in the buffer. Okay, because the spare room changes with time, the free buffer space here changes with time, so this value is also dynamic. And for the congestion control, okay, although some of the books use congestion control and flow control interchangeably, but somehow in my slide, flow control means different from the congestion control. Congestion control is a mechanism and technique to control the congestion and keep the load below the capacity. So network congestion control, the purpose is to avoid network overload. This is when the load reaches the network capacity. So as I have said before, each network has its own capacity. So by using the network congestion control, it can avoid network overload from happen. It also prevents packet loss at router buffers in the network. This is because when the buffer at the router is full, the packets will be discarded. So somehow the packet will be lost. Network congestion control also serves the purpose of fair sharing of rates between all TCP connections on the bottleneck link. So what is bottleneck link? For example, here, this is the bottleneck router, okay, with the capacity R. Means that this router is shared between two TCP connection, which is TCP connection 1 and TCP connection 2. So if these two TCP connections share the same bottleneck link of bandwidth R, so each should have average rate of R divided by 2, because there are two TCP connections. Let's say if we have K TCP connections, okay, sharing the same bottleneck link, so the average rate of TCP connection should have R over K. Okay, so this means the fair sharing of rates between TCP connection on a bottleneck link. Besides fair sharing, it also provides elastic traffic, means that connection bit rate can vary according to the available capacity. Or in other words, it is more flexible to whatever the network can offer. There are several issues with the flow and congestion control, so we will look at the issues one by one. For the flow control issues, first we have a zero window probing issue, or in other names we can call it window shutdown. So what happened during zero window probing? Receiver will temporarily shut down the window by sending RWND value of 0. This means that receiver does not want to receive any data from the sender for a while, and this will make the sender stops sending data until a new advertisement has arrived. So for zero window probing, a TCP may keep its offered receive window closed indefinitely. So as long as the receiving TCP continues to send acknowledgements in response to the probe segments, the sending TCP must allow the connection to stay open. Another issue is silly window syndrome avoidance. Okay, so for this issue, the network use the capacity very inefficiently. Okay, it is actually a situation in which a small window size is advertised by the receiver, and hence a small segment will be sent by the sender. So this sender will create data slowly, or receiver will consume data slowly, or both. So the network will be used very inefficiently in this case. Okay, so I give you an example. If TCP segments contain 1 byte of data, it means that for a segment, 41 byte datagram, 20 bytes of TCP header, and 20 bytes of IP header transfers only 1 byte of user data. So we recall that TCP header has 20 bytes and IP header has 20 bytes. So header here is more than 1 byte of data. So this is inefficient of the network use. So it is even worse if we count the data link layer and physical layer overhead. So this congestion control problem and task is to give stability to the connection of the network, and also to give the fairness in which the average transmission rate of each connection must be equal, or at least each connection can get equal share of the link bandwidth according to its specific usage. Moving on to the next slide, we are going to learn a new term which is called TCP sliding window. Okay, a sliding window is an abstract concept that defines the range of sequence number that is the concern for both sender and receiver. Okay, in other words, the sender and receiver need to deal with only part of the possible sequence number. So the purpose of this sliding window is to make transmission more efficient, and also to control the flow of data so that the receiver does not become overwhelmed with data. Means that the receiver does not receive too many data that it cannot process. So transmission window here is determined from minimum of these two values. Either it is advertised receiver window, which we have been introduced to this term before, and also congestion window, or CWND. So this window size is determined by the minimum of these two values. So this is the concept, the abstract concept of the TCP sliding window. So the receiver window here is the value advertised by the receiver in a segment containing acknowledgement. Okay, so the receiver advertised RW and D value. It is the number of bytes that the receiver can accept before its buffers overflows and data are discarded. The congestion window, on the other hand, is a value determined by the network to avoid congestion. So here is a sliding window. The window here can be opened, closed, or shrunk. So these three activities, as we will see, are in the control of the receiver, and also depends on the congestion in the network and not the sender. So the receiver controls this thing. Okay, the sender must obey the commands of the receiver in this method. So for opening here, we can imagine that this window is open to allow more new bytes in the buffer that are eligible for sending. So this window can also close, which some bytes have been acknowledged, and sender need not to worry. Shrinking, which shouldn't happen, means that moving this right wall to the left, which is controlled by the receiver. Shrinking is strongly discouraged, and it is not allowed in some implementations because it means revoking the eligibility of some bytes for sending. So we can imagine this is the things in the buffer. So this is the part where the packets have been acknowledged, okay, by the receiver. This is the part at which the packet is going to be acknowledged by the receiver. Okay, let's see some examples of the sliding window, okay, from the sender's perspective and also from the receiver's perspective. So in this example, it is assumed that the use of 3-bit sequence number. So that is why the frame here is being numbered from 0 to 7. Okay, so we have basically 1, 2, 3, 4, 5, 6, 7, 8 frames, okay, which is 2 power of 3. So that is why 3-bit sequence number. So the shaded rectangle here indicates the frames that may be sent in this. So in this figure, the sender may transmit 1, 2, 3, 4, 5. 5 frames beginning with frame 0. Okay, so each time a frame here is sent, okay, the shaded window here will shrink, okay, from the trailing edge. So each time acknowledgement is received, okay, the shaded window here will grow. So frames between the vertical bar here and also the shaded window here, okay, it shows that the last frame transmitted and the frames that is waiting for the acknowledgement to be sent. Okay, means the frames buffered until acknowledged. So this part here show the frames that are already transmitted. At the receiver's perspective, this shaded window here shows that window of frames that may be accepted. Okay, so window will shrink from the trailing edge here as frames are received, and a window will expand from the leading edge here as acknowledgements are sent. Okay, on the contrary from the sender's perspective. Okay, so this is number 7 here is the last frame received. Okay, it is both of frame number 6 and 7 are buffered until acknowledged. Okay, so this is the last frame acknowledged, and this shows the frames that are already received. So this is from the receiver's perspective and this is from the sender's perspective. Okay, so this is an exercise that we are going to do. For example here, what is the value of the receiver window for host A if the receiver for host B has a buffer size of 5000 bytes and 1000 bytes of received and unprocessed data? Okay, so given these two values, you can easily determine the receiver window size. Okay, so the receiver window size here is 5000, which is the buffer size, okay, of host B, and 1000 bytes have already received, okay, and the value of the receiver window is thus 5000 minus 1000 equal to 4000. Okay, means that B can receive any 4000 bytes before the buffer overflow. Okay, another question. What is the size of the window for host A if the value of receiver window or the RWND is 3000 bytes and the value of CWND is 3500 bytes? So remember the equation, we need to take the minimum value of these two values. Okay, so the answer here is 3000 bytes. Okay, window size is equal to 3000 bytes because we take the smaller one. So the next part is congestion policy. Okay, for the congestion policy, okay, this is a very important part to determine the TCP performance. Congestion policy have several phases that you need to know. The first one is slow start, okay, and then the next phase is congestion avoidance and also congestion detection. So the decision to go to any of these phases depends on the current condition of the network. Okay, first we have a look at the slow start, or in other words, exponential increases. So for slow start, the sender starts with a very slow rate of transmission and increase rapidly to reach a threshold. So the idea here for the slow start here is the window will start slowly and it will grow exponentially. Okay, and the next phase is congestion avoidance. Congestion avoidance happen when the threshold is reached, and thus the data rate will be reduced to avoid the congestions. Okay, for the congestion detection, the sender will goes back to the slow start, okay, to this phase, or to the congestion avoidance phase based on how the congestion is detected. So this rate is being controlled via the transmission window size. So we're going to look at the example for the congestion policy here. Okay, so this is the example, okay, from sender to the receiver for the first phase, which is the slow start in the congestion policy. So in this example, okay, we will have to assume that CWND is smaller than RWND. Okay, so I repeat, we will assume here the congestion window size is smaller than receiver window size. Hence, the sender window size, we will take the minimum one, which is the CWND or congestion window size. Okay, so the size of the congestion window size at the beginning, okay, of the transmission, it will begins with 1 MSS. MSS. So MSS here means the one maximum segment size. Okay, MSS here means maximum segment size. So this MSS here is determined during the connection establishment. Okay, so size of this is 1 MSS. Size of this 1 MSS, okay, size of this CWND increases 1 MSS each time an acknowledgement is received. So we look here, okay, the first one, CWND is equal to 2 power of 0, which is 1, okay, 1 MSS. So segment 1 is being sent to the receiver, and when the acknowledgement is received, this is considered round 1, or some of the books also use as RTT1. RTT. Okay. So after the first acknowledgement has been received, the CWND size is increased to 2 MSS, which is 2 power of 1. So because of that, 2 segments are being sent before we can consider the second round is completed. So the first segment 2, the acknowledgement 3, the second segment, which is segment 3, okay, second segment for the round 2, which is segment 3, and acknowledgement 4 is received. So this completed the second round, or RTT equal to 2. And then after the second round, the CWND value will be increased to 2 power of 2, which is 4. Okay, 1, 2, 3, 4. So this means that 4 segments can be sent for the next round. So the first segment, acknowledgement 5, the next segment, acknowledgement 6, the segment 6, acknowledgement 7, the segment 7, and acknowledgement 8. Okay, so if you see here, for each acknowledgement received, the CWND size will be increased by 1. So by the end of the round 3, the CWND value has become 2 power of 3, which is 8. So here, this is 8. So, in short, we can say that at the beginning, the CWND is equal to 1. That is, TCP only allowed for the sender to send one segment and must wait for an acknowledgement before transmitting a second segment. Okay? So, after round 1, CWND is equal to 2 because each time an acknowledgement to new data is received, the value of CWND will increase by 1. As we can see here, each time acknowledgement is received, it will be increased by 1. So after round 2, CWND is equal to 4, and after round 3, CWND is equal to 8. Okay? So in effect, these slow start mechanisms probes the internet to make sure that the TCP entity is not sending too many segments into an already congested environment. So as acknowledgement arrive, TCP is able to open up its window until the flow is controlled by the incoming acknowledgements rather than by CWND. Also, it can be noticed that this all process results in the doubling of the sending rate for every round or for every RTT. Okay, so thus the TCP send rate starts very slow, okay, but it grows exponentially during the slow start phase. So it is also worth to mention that when the value of CWND here equals to slow start threshold or SS thresh, slow start will end and TCP transition will be transitioned into congestion avoidance mode, which we are going to have a look after this. So the next phase is congestion avoidance or additive increase. Okay, so when the CWND size is equal to slow start threshold, okay, slow start phase will stop and this additive increase phase will begin. Okay, so in this additive increase phase, the CWND value will be increased by 1 every RTT instead of increase exponentially, okay, just like the slow start. So in this phase, it will increase only by 1. Okay, if we look at the example here, okay, if we look at the example here, the sender will send the first segment to the receiver and the receiver will send acknowledgement to the sender, which it expect the second segment will be sent, okay, by the sender. So upon receiving the acknowledgement to, the CWND size will increase by 1. Okay, it means that there are 2 segments that the sender can send to the receiver. So the sender will send 2 segments, okay, and receiver will also send 2 acknowledgement to the sender. So after acknowledgement 4 are received by the sender, means 2 acknowledgement are received at the round 2 or RTT2, the CWND size will be increased by 1, okay, not by exponentially, just like slow start before. For this additive increase, it will be increased by only 1. So for the next round, only 3 segments is allowed to send by the sender. So the sender will send 3 segments to the receiver, and the receiver will send acknowledgement by another 3 acknowledgement segments, okay, to the sender. So upon receiving the third segment at round 3, so the CWND size will be increased by 1. So the new size now is 3 plus 1 equal to 4. To sum up, for the congestion avoidance phase, every 1 round trip time, CWND will be increased by 1. So after the first round, for the first round, CWND is only equal to 1. And the next round, it becomes 2. And finally, after third round, okay, 3 RTT, the CWND is equal to 4. In the next example, I'm going to show you congestion phases from the slow start to additive increase, and the next one is multiplicative decrease. So the decision whether from the slow start to go to the next phase, which is the congestion avoidance or additive increase or multiplicative decrease, depends on the congestion detection. Sender can guess the congestion has occurred by the need to retransmit a segment. So retransmission can occur in one of these 2 cases. The first one when the timer times out, and the second one when there are 3 duplicate acknowledgements are received by the sender. So for the first case, if detection is by timeout, a new slow start phase will begin. Okay, and however, if the detection is by 3 duplicate acknowledgement, this will show the weaker possibility of congestion. a new congestion avoidance phase will start. Okay, so for this possibility, a segment may have been dropped or some segments may arrive safely since 3 acknowledgements are received. Okay, if we look at this example, this is the congestion window size versus the number of rounds. Okay, let's say here the MSS is given as, okay, let's say here the maximum window size, okay, which is MSS, is equal to 32 segments. So this is only for this example. So this means that the threshold here is half of the MSS, which is 1/2 multiplied by 32 segments is equal to 16 segments. Okay, so let's start here from the beginning of the round. We know already how we can get this threshold number, which is half the given maximum window size, which is MSS. So MSS is actually determined by the maximum transmission unit of the network. Okay, so given MSS is equal to 32, we get the threshold is equal to 16. So at the beginning of the slow start phase, the number of CWND size grows exponentially from 1 to 2 to 4 to 8 until it reaches 16, which is the threshold of the congestion, okay, a slow start threshold. Okay, after it arrive threshold, okay, it will begin the congestion avoidance phase, which is the AI phase, additive increase. So with that, the CWND size will increase 1 at every round. Okay, so from round 5, it will increase by 1, round 6 by 1, up until round 8. Okay, so in this example, it can be seen that timeout occurs. Okay, means that the timer times out. Okay, so here, listen carefully. As I have said before, when the timer times out, okay, a new slow start phase will start, and hence the CWND size window will goes back to 1. Okay, so I repeat here, the CWND size or congestion window size here will goes back to 1. Okay, so timeout here occurs at round 8, in which the congestion window size is at size 20. So from here we can calculate the new threshold size, which is half of the size at which timeout occurs. So here, when timeout occurs at 20, the threshold size here will become half, which is 1/2 multiplied by 20, which is equal to 10. Okay, at round 8, the slow start begins. So at round 9, it will grow, the congestion window size will grow exponentially to 2, to 4 at round 10, to 11, to 8 at round 11, and at round 12, it will reach the threshold, which is 10. Okay, so once the congestion window size reaches threshold, it will begin back the additive increase or congestion avoidance phase. So by then, after round 13, the size of the congestion window is only increased by 1. Okay, and the next at round 14 here, the congestion window size is around 12. Okay, so suddenly here at round 14, the retransmission occurs because of 3 duplicate acknowledgements have been received. So this indicates weaker possibility of congestion, and hence multiplicative decrease occurs, but somehow it will goes back to the congestion avoidance phase, okay, or additive increase instead of slow start. We should notice also that these 3 acknowledgements received when the congestion window is at size 12 and round 14. So what happened next is the congestion window size will be decreased by half of the current window size. So half of the 12 means if it goes back to 6, okay, before it will start the congestion avoidance phase again, where the congestion window size will be increased by 1. Okay, so I hope you understand that is basically what happened in this congestion example. So I will summarize it again here. Okay, from the first round, the slow start phase happens up until threshold 16 is reached. Okay, and then the new phase, which is the congestion avoidance phase, okay, or additive increase, will happen up until time out at congestion window size equal to 20. So now it will begin back the slow start phase with the threshold of 10, which is half of the size 20 at which time out occurs. And then upon reaching the threshold equal to 10, another additive increase phase will begin, okay, up until round 14, where there are 3 duplicate enrichment received. It will goes back to half of the current congestion window size, which is 10. So half of 10 is 6. It goes back to 6. The congestion window will go back to 6. And the new additive increase phase will happen, okay, will take place, and the congestion window size will be increased by 1. Okay, so this is basically what happened in this example. Okay, so here is your task. Okay, for this example, you need to answer this question, okay, based on the given congestion window size here versus RTT, and you need to upload the answer for this task on the e-learning as a proof of your attendance, means as a proof that you have watched this video. So there are 2 tasks for you. The first task here, okay, you can just answer straight on the e-learning, or you can answer on the a piece of paper and take a picture and convert it to PDF and upload on the e-learning. Okay, so the next task here is task 2. Also, you need to answer the question. It's okay if you don't get it right. I will give you the comments for each of your answers. Okay, so this also you need to upload on the e-learning. Okay, so there are 2 tasks, task 1 and task 2. Okay, so that is all for our subtopic, which is the TCP performance. So until then, I will see you again in the next online video learning. Thank you.